Where do we come from? Or even better, where does everything come from? Images like these from the recently launched James Webb Space Telescope aren't just beautiful. They help scientists answer some of the most fundamental questions humans have ever asked. Why does our universe look and work the way that it does? Now, this image is one of my personal favorites because every single dot, smudge, and blob in this image is a whole galaxy, every single one. And each of these galaxies have millions, if not billions of stars in them, and probably that many planets too. The reason why the galaxies in this image are so small is that they are very, very far away. The galaxies that I've circled here are approximately 10 billion light years away. That means it took the light from the stars in those galaxies approximately 10 billion years to reach our telescope. So astronomers can use these large distances and the finite speed of light as a sort of cosmic time machine, reaching back into the earliest moments of our universe's history. So that means we aren't seeing these galaxies as they exist today. We're seeing these galaxies as they looked when they were just being born. But how are galaxies born? Fundamentally, galaxies form from the competition of two forces. Gravity pulling gas together from the primordial plasma that filled our early universe, which in turn gravitationally collapses to form that galaxy's stars, and an outward pressure. That pressure is dominated by the violent cycle of life and death performed by the galaxy's stars. When stars form, they come in a whole range of masses. And while the smaller stars, like our sun, are more common, it is the rare, massive stars that are hugely important to the evolution of galaxies. These stars are the live fast and die hard crowd. They exist for a mere fraction of the time of their smaller counterparts, but they are the game changers. These most massive stars only exist for a mere 10 billion years. Now, that may seem like a long time to you and I, but that's basically a flash in the pan when it comes to the rest of the universe. Our own sun is middle-aged, given its expected lifetime, and it's already been around for 6 billion years. So 10 million years is practically nothing. When we look at the beautiful images and stars that fill our night sky, we don't often think of violence. But all stars, when they are young, create violent winds that help shred their birth clouds. And when the most massive stars die, they create explosions. And those explosions are called supernova. Each supernova releases about as much energy as the sun produces over its entire lifetime in mere seconds. And in the days and weeks after that star dies, the explosion outshines the combined light from all of the billions of stars in its host galaxy together. But in young galaxies, it's not just one star going supernova every 50 years or so, like in our own Milky Way. In young galaxies, stars form and die at rates hundreds to thousands of times faster than that. So multiple supernova are exploding at nearly the same time, and often in close proximity. The combined effect of these explosions creates superwinds that blast the dust and gas out of the galaxy. These winds contain the remnant ash of the nuclear fusion that powered the stars when they were still alive, as well as anything that got created in the violence of that explosion. To quote the late, great Carl Sagan, that ash is the carbon in our trees, the oxygen we breathe, the nitrogen in our DNA, the silicon in our computers, and the gold in our jewelry. So these violent deaths are also a rebirth, because we would not be here today on this earth if were not for the nuclear furnaces of previous generations of stars and their violent deaths. So galaxies are created by this stellar evolution, and we see the lasting effects of these life cycles all around us. And while I've painted a pretty picture so far, albeit a pretty violent one, we don't have all the answers yet. Why do these galaxies in the early universe form so many stars so quickly? Is it the same process that happens today in nearby galaxies, just scaled up because there's more gas around to fuel that star formation? Or is something fundamentally different going on? And what ends this violent cycle of stellar creation in these galaxies? So if we want to understand the beautiful diversity of galaxies that exist today, their sizes and shapes, their colors and their dynamics, we need to understand star formation across cosmic time. The challenge is that stars are actually pretty tiny when you think about it. And I cannot emphasize enough the sheer scale and ranges of the scales that exist in the universe. For example, a massive evolved star like Betelgeuse may be 750 times larger than the Sun, which is in turn 100 times larger than the Earth. But it would take 37,000 Betelgeuses stacked next to each other to span the distance between us and the next nearest star to Earth. And then it would take 6,000 times the distance between us and that star to reach the center of our galaxy. And then it would take a mere 95 times that distance to reach our nearest galaxy neighbor, Andromeda. And then it would take 1,600 times that distance to reach the nearest galaxy in my favorite James Webb Space Telescope image. So when they call very large numbers astronomical, they weren't joking around. So what can we do? How can we possibly study star formation within galaxies that are 10 million times further away than the largest of the stellar birth clouds? Well, the first answer would be to build a bigger telescope. But that is a costly and time-consuming enterprise. The James Webb Space Telescope took 21 years from community selection to launch, and that's ignoring all the years of development that occurred before then. And that ultimately cost $10 billion to construct, which took us from this to this. So it was definitely worth every penny. But if these galaxies are still mere blobs, even to the James Webb Space Telescope, imagine how many years of construction and technology development is necessary to resolve these galaxies nearly as well as we can for nearby galaxies. So what can we do? Luckily, nature gave us a trick: gravitational lensing. Thanks to Einstein, we know that mass warps the fabric of space-time, and when light travels, it follows that curvature. However, our eyes and telescopes don't know the full history of that galaxy's light travel. We only know which direction the light was coming from the instant before it hits us. So if we extrapolate backwards, the object emitting that light may look like it's over there, but really, it's over there. This displacement is known as gravitational lensing. So if we have two galaxies closely aligned with our line of sight, the foreground galaxy's mass warps the path of the background galaxy's light. That makes the background galaxy appear offset, distorted, but also magnified. So if we specifically study gravitationally lensed galaxies, we will get higher physical resolution of the processes within those galaxies than we would have otherwise. And luckily, gravitational lensing is not that rare. The universe is vast, and there are so many galaxies out there that the correct alignments definitely happen. The trick is just finding it amongst all that vastness of space. This is one of those things where algorithmic development has helped a lot. Thanks to the application of machine learning, we now know of millions of lensed galaxies. And so by following these low resolutions up with detailed multi-wavelength observations, we will finally be able to dissect the processes occurring within them and understanding these galaxies' extreme cycle of stellar life and death. This work is only just beginning, and who knows what we will discover about our universe's fiery past. Thank you.